So here's the deal now. We have a data that says the science tells us that it should be exponential in 1 over t, not in t itself. If we tried to fit this data to t itself, might not be such a great fit. So what we do is we create another column and we do a calculation, 1000 divided by t. So we expect that this is going to be exponentially, this would be our x-axis data, and it's already plotted. This would be our y-axis data, again, already plotted. And if we modeled this as an exponential, everything ought to work out. In fact, we know if we change this over here, for example, to a logarithmic scale, that it ought to appear to be a straight line. This is what's called transforming the data, linearizing the data. We're finding a model where we can use our linear regression to fit. Wow, it is a nice linear fit. Okay, I'm going to get out of that, and we're not going to do the exponential, the logarithmic scale on the y-axis, since we see that it's a nice straight line. We're just going to do an exponential fit. So let's just add in our trend line. Since it looks so nice as an exponential, everything ought to be hunky-dory. Okay, exponential. And voila. Display equation, display this, and we're ready to rock and roll. And where's the equation? It's nice, teeny tiny. We'll make it big and fat. There. And we do, let's go ahead and format the numbers on this too. Format trend line label. Let's make it exponential. Let's make it, since we got 4.887 in the exponent, let's make it a scientific number with 3 decimal places. There we go. And move the box. Okay. So now we get our nice, neat numbers. Let's take a look at what this equation is really telling us. X is way over here on the far right-hand side, right over here. So we're getting the reaction rate. Good. Reaction rate equals some number, which in this case is 2.867 times 10 to the 7th, E, Euler's number, raised to the some number B, times 1,000. Remember, the x-axis is 1,000 divided by t. If I went to 1 over t, I would have numbers like 0.0003, 0.00031, and so on. 1,000 divided by the temperature gives me nice numbers in the range of 3 to 4. Here it is, 1,000 over t. You'll see this commonly in chemistry. You'll see this commonly in engineering, because this is a model that we see a lot. A lot of chemical processes, metal alloying, things like that, are are based on what this is called. It's called an Arrhenius model. So there we go. So this is the actual equation because we've made x equals 1,000 over the temperature in degrees Kelvin. So this is what's called transforming the data. It's taking nonlinear data and you're coming up with an equation to make it linear so that you can use the power of linear regression inside of Excel to get a nice, neat fit based on science. You might have to take v squared, you might have to take v, you might have to do other things like that to transform the data. I just want to look at one more data transformation. Here we have a chart on ozone data, the ozone hole. It's curvy. It's not a neat curve. It's not logarithmic. It's not exponential. We don't expect it to follow any science because back in 1994, we did some things like eliminating chlorofluorocarbons and things like that so that we could get a nice, healthy ozone layer back. So mankind took some action to get the ozone, to reduce the ozone layer depletion down to next to nothing. So we don't expect it to fit a scientific model, so polynomial is probably as good as it's going to get on this one. So let's put in a trend line. And a polynomial, there we go. Is this second order? Probably it's going to be third order, maybe fourth. Fourth looks pretty good. You want to keep the number of orders down as much as possible. Now let's see what the equation looks like. There's the equation, and like always, it's really tiny, so let's make it big and fast so you guys can see it. There. Now we get numbers like, we get tiny numbers and numbers here and 10 to the 9th and maybe, yeah. So we get some kind of crazy numbers, which is probably a better idea to turn it into scientific. But before I do that, I'm going to do another change. Let's just delete the trend line. In fact, I'm going to delete the whole chart. Let's just delete the whole chart. We're going to do something a little different. Come on, chart, go away. Now we're going to use a polynomial. We kind of figured out that's probably about the best fit. But let's go years since 1995. So we're going to transform the data a lot like we did before. So it's going to be this minus 1995. There we go. I'm going to do an auto fit just so you can see everything and copy and paste my formula down. Again, Excel is going slow. You know, everything's on the cloud now, which means everything's slower because you got to send data back and forth on a network, just like a web page, which just slows everything down. Oh, come on. Okay. I wish you could just work offline if there's an option for working offline and not screw with the quote cloud. Okay, so now we have our data. We select it on up. We insert our chart. Gonna make it nice and bigger. There's my handles. Get it nice and big for you guys. Now let's insert the trend line. And what did we decide x cubed was about the best? I can't remember. Polynomial. Oops, 3 or 4. 3 looks, no, 4 looked a lot better. Okay. And now we display the equation. It should have nice rounder numbers. It shouldn't be so crazy tiny numbers. Yeah, they're not a lot nicer. They're a lot rounder. They're a lot they're easier to read. And I'm going to give it scientific. All right, I could go scientific notation. I'm going to give it, though, 1, 2, 3, 4, 5. I'm going to give it 6 decimal points and make it a number. Give it 6 decimal points. That'll make sure I have 3 significant figures on each number. Okay, there we go. And why didn't it? I must have hit the wrong button. There's 6 decimal places, at least 3 significant figures on each number. And just so you guys can see it, I'll just have to make sure that it's nice and big. That's the last thing I wanted to show you from this chapter on fitting. You might have to transform the data like I just did, or like the one I did previously. Or you might need another data transformation like the square root of x or something like that. You might need to transform y instead of x. You're going to have to play with it to try to work the math so that the theory has some sort of linear, that some function of y equals m times a function of x plus b. That's what you're striving for. And then once you can do that, you can plot function of y versus function of x, and you should get a nice straight line and be able to fit it using the techniques we learned in this chapter. That's the goal. And if you can't, you got to go to nonlinear fitting. There's techniques to do that. It's a lot harder. So if you can linearize the data, you'll be a lot better off. And these are just a couple examples of linearizing the data. Okay, that's it for this chapter. On to chapter 8 next. This is the end of chapter 7.